Great. Yeah, I think we're ready to go now. So, while I'm launching this program, I'll suggest one of our teaching staff, can you please check the lobby and admit people as long as they are joining here? Hello, everyone, all distinguished participants, esteemed colleagues and partners. Good morning, good afternoon, good evening from Melbourne, Baghdad, Dubai, Beijing, Mumbai, and every corner of the globe from which you are joining us today. So, it is our great privilege as a program chair to welcome you all to the ATIS 2025 training program on quantum programming and techniques for information security. This is a pioneering 5-day journey into the quantum foundation that will define next generation of secure intelligence system. We all stand at crossroads. Right now, quantum computers at IBM, Google, and several other research labs worldwide are scaling towards threshold that will break the encryption protection of our banks, of our hospitals, several government sectors, and communication. RSA, which has been a backbone of the internet for a long time now, will definitely fall down after some time. So the countdown has begun, but there is a huge opportunity here. Quantum does not just break security, it reveals and make it more stronger. So quantum key distribution offers some kind of unbreakable communications, as you people might have already heard of different enhancements ongoing. There are several other advancements in the area, including quantum federated learning, enabling privacy, preserving AI across borders and across institutions. The question is no longer whether quantum will transform security and computing aspects, but we'll master it first and we'll mm, gain into the advantage of or upskill themselves first. That's why we all are here. This program is our launchpad. It is completely a 5-day workshop. It can be very informal in terms of teaching and learning aspects. But why ATIS is offering this is because it is global, it is strategic, it is cross-border. We are proudly supported by Australian Government Council for Australia-Arab Relations. And then this is being delivered by Deakin University in collaboration with University of Kufa, Mohammed bin Zayed University of AI, and Zayed University. It's great for you to be the part of this strategic initiative and shaping quantum talent and intelligence across the continents. Mm, as we have outlined and send you email through the workshop guide, you may have already noticed how the program is built up and how we are going to deliver this workshop. Uh, to be very specific around it, we normally use forums. Almost all of the sessions are recorded. You have a separate discussion channel which we are going to post here after some time, so you can raise your concerns, questions, and then you can discuss with other attendees in the discussion forum in parallel. The discussion forum will be there for the all 5 days and throughout 24 hours, so you can jump in and write down your queries and questions at any point in time. Please check your email daily for the links, updates, and material. Reach out to our teaching staffs for help takes and forums. There are several daily mini tax deadlines. You need to understand, grasp the ideas, and then um, conduct, perform it based on what your tutors or teachers will be instructing you. So there are some grace periods available too. You can reach out to our teaching team. So you are not just the learners here. You are the architect of quantum computing and secure future. So this is your moment. This is your quantum leap. Welcome to ATIS 2025. So with this, I would like to mm, hand over to our teaching team. But I'm happy to take any queries if you have anything regarding the admin or regarding uh, other aspects of ATIS apart from what
It
has
is
already
actually
been. Yeah, apart from what has already been communicated to you through emails. So I'm going to open the floor for around 5 minutes, and then our teaching starts can get ready with the offerings that we have planned for day one. Any questions? Yeah, if you don't have any questions, I'd like to provide a very informal basis on what makes us to offer such a prestigious training program through ATIS is because we are in a race of preparing future researchers, future innovators. Through these programs, we want to prepare students for the research, basically for those who are not connected, well connected with the Australian community, and bring them as PhD students into the programs or postdoc or research assistants into the programs as well. So this is the main vision, mission, and goal of these programs. Either as a PhD students or as industry researchers in the area. Any questions? If you have any questions, please raise your hand. Great. So I'd like to introduce our teaching team. So we have a big cohort of quantum expert as our teaching team uh, into ADIS. I'd like to thank all of them for contributing for teaching. And then um, I will suggest all of our teaching team, can you please unmute yourself and introduce? I can quickly go through the name list. Sanika, you can go first, and then Dave, and then Navneet, and then Devasis, and then Swati, and then Bovo. Hi, Sanika, you are here?
Yeah, I'm here. Hi. Hello all. So, I hope you can see me, no?
We cannot see you, we can hear you.
Okay, that's fine. So, hi all. I'm Shani Kairoshi Nanayakara. I'm attached to the quantum related research lab here in Deakin, and I think you will be able to gain a huge capacity of knowledge about the quantum in coming up days. So, uh, Uh, actually, I want to. I will come up with you in the next couple of days, and yeah, welcome all. Thank you.
Thanks, Sanika. Dave, Dave, you are muted. Devasis,
Yeah, hi everyone. I am Devashish Chaudhary, a second year PhD student, and I am currently working in anomaly detection using quantum federated learning. So, yeah, welcome you all to this wonderful program.
thanks, Devasis. Navneet,
Hi everyone, my name is Navneet Singh. I'm researching around quantum machine learning and its applications, and I'm hoping you will learn something good from this 5 days. And hope and happy to collaborate with you guys. Thank you.
thanks, Navneet. Swati,
Hi everyone, I'm a researcher with Deacon's Quantum team. I'm working with quantum machine learning and anomaly detections. I hope you all get good worth content out of this course that we are prepared for you, and I hope your queries encourage us to learn better too. Thank you.
thanks, Swati. Bobo,
Hi everyone. I'm a second year PhD student in the University of Technology, Sydney. And for my research areas, it includes the privacy protection for quantum computation. So I will introduce some basic concepts around this privacy in the quantum computation in the 5 days. And if you're interested in this field, very glad to discuss something with me.
Thanks, Bobo. So, Dave, are you here?
Hi everyone. My name is Dev Gurung. I am working on quantum federated learning at the moment. So, yeah, welcome to this program. I hope you guys would get some good experience on Qiskit if you have no experience with the Qiskit or I hope this program will be productive for everyone. So, yeah, thank you everyone.
Yeah, thanks, Dave. So, with this introduction of our teaching team for the 5 day seminar, I'd like to kick off today's training session. Uh, in the meantime, uh, we'll quickly check our discussion board if there are any concerns roaming around there. I'll also put a link in here so attendees can start putting their queries in the discussion board. So, who is the first presenter for the day? Can you please come up with your slides and then start the technical session, please?
Yes. Yeah, is it visible?
Yeah.
Yeah.
Yes.
So, hi everyone, I'm Devashish Chaudhary, and today I'll be talking about some basic concepts of quantum computing. So, let's start with a simple question like, what is quantum computing? Today's classical computers, whether it's your laptop, your phone, or even the most powerful supercomputers, are incredibly fast and capable, but they still have some limitations. When the amount of data becomes extremely large or when the calculations become very complex, even these powerful machines begin to struggle. Some problems grow so quickly in complexity that a classical computer would take years or even centuries to solve. This is where quantum computing comes in. It uses the unique principles of quantum physics, such as superposition, entanglement, and inference, to process information in a completely different way. We'll go deeper into these principles in upcoming sessions. And quantum computers are still in the early stages, but the field is evolving rapidly every day. So now let's talk about the evolution of quantum computing. The idea of quantum computing actually began taking shape in early 1980s when physicists realized that the strange principles of quantum physics could be used for computation. This sparked a new line of thinking. What if we could build computers that follow the laws of quantum mechanics instead of classical physics? A major breakthrough came in 1994 with the development of Shor's algorithm. This algorithm showed that a quantum computer could, in theory, break many of the encryption methods that we rely on today. It was a powerful demonstration of how different and how much more capable quantum computing could be for certain tasks. But at the same time, the algorithm existed only on paper. The hardware needed to run it simply didn't exist at that moment. During 2000 to 2010 era, small quantum hardware systems began to appear in research labs. Scientists were experimenting with different ways to build qubits using ions, photons, and other quantum particles. These early devices were purely experimental and extremely unstable. They worked only under very controlled conditions and even then only for very short periods of time. Then came the 2010 to 2020 decade when major technology companies like Google, IBM, and Intel entered the field. Quantum hardware started to scale. Instead of just a few qubits, systems grew to dozens. A major milestone came in 2016 when IBM introduced the first cloud accessible quantum computer, allowing researchers, students, and developers around the world to experiment with quantum computing for the very first time. Now, in the current era, quantum computers are still very noisy and far from perfect. They can't solve large real world problems yet, but they can be used for research, education, and early stage applications. These machines are helping scientists to learn how to correct errors, improve stability, and move closer to truly powerful quantum computers. Now let's look at how classical bits differ from qubits, which are the basic units of information in classical and quantum computers. Classical computers use bits, and each bit can be either 0 or a 1. By performing operations on these bits, classical computers process information and produce results. Quantum computers, on the other hand, use qubits, which is also called quantum bits. A qubit can be 0, 1, or a superposition of both 0 and 1 at the same time. We present this mathematically as psi equals alpha times 0 plus beta times 1. Here, alpha and beta are numbers that determine the probability of measuring the qubit in state 0 or in state 1. And importantly, the sum of the squares of the magnitudes must equal to 1. To visualize this, think of tossing a coin. While the coin is spinning in the air, we don't know whether it will land on heads or tails. That uncertainty is similar to a qubit in superposition. Only when the coin lands, just like when we measure a qubit, um, we get a definite outcome, which is either 0 or 1. We can also visualize a qubit using something called the block sphere as shown in the left figure. In this sphere, the north and south poles represent the classical states 1 and 0. So when a qubit is placed in a superposition, its position moves somewhere in between these poles, which you can see as the pink line shown here. The x and y axis of the sphere represent the phase of the qubit. A qubit in superposition can lie anywhere along the equator. While the phase doesn't change the probability of measuring 0 or 1, it becomes very important when qubits interact or when we apply quantum gates. Now let's look at a simple example of Qiskit, a Python library for programming quantum circuits, which is shown on the right hand side. The first line imports the Qiskit library, and quantum circuit 1, creates a circuit with one qubit and one classical bit. The classical bit is used to store the measurement result. And when we measure using qc.measure 0, 0, it measures qubit 0 and stores the result in classical bit 0. And in this example, we measure the qubit. We always get 0. This is because a qubit is initialized to the 0 state by default. To put the qubit into superposition, we would apply a Hadamard gate before measuring it. Only then would repeated measurements would show a mix of zeros and ones. Now let's move on to Dirac notation, also known as bracket notation. Dirac notation is a very compact and neat way to represent quantum states. Earlier, when we wrote psi equal alpha 0 plus beta 1, we were describing the superposition state of a qubit. In this expression, psi is called a ket, and a ket is simply a column vector. Every ket has a corresponding bra, which is the complex conjugate transpose of the ket. You can see how a bra notation is written and is represented as a row vector. Bracket pairs are extremely useful because they allow us to compute the inner product between two quantum states. In the matrix form, the ket 0 is written as 1, 0 as a column vector. The ket 1 is written as 0, 1 as a column vector. So the superposition state psi in matrix form is simply the column vector alpha and beta. Direct notation becomes especially powerful when we start working with multiple qubits, quantum gates, and inner product calculations because it keeps everything clean, simple, and easy to manipulate. For example, let's look how inner products work using bracket notation. If we take the inner product of 0 with 0, we get 1. This is because the two states are identical and they completely overlap. But if we take the inner product of 0 with 1, we get 0. That's because these two states are orthogonal, or in simple terms, they are completely different and have no overlap. This idea of overlap or similarity between quantum states is fundamental in quantum computing, and bracket notation gives us a clean way to compute it. Now let's look what happens when we put a qubit into an equal superposition of 0 and 1. In this case, the values of alpha and beta both becomes 1 by root 2. So the state of the qubit is written as ket psi equals 1 by root 2 ket 0 plus 1 by root 2 ket 1. To find the probability of measuring the qubit in each state, we square the magnitudes of alpha and beta. Since alpha and values of both alpha and beta are 1 by root 2, the probabilities are 50% chance of measuring 0, 50% chance of measuring 1. This means the qubit has an equal likelihood of collapsing to either state when measured. The code on right hand side shows a simple Qiskit example. The first line creates a quantum circuit with one qubit. We apply Hadamard gate, which is also called H gate, which places the qubit into an equal superposition. We then measure the qubit and a simulator is initialized and the circuit is run for 1024 times. These repetitions are called shots. Running the circuit many times is important because if you measure the qubit only once, you will see only a single outcome, which will be either 0 or 1. But when you run it for 1024 times, you start to see the underlying probabilities. So in this example, out of 1024 shots, the simulator returned 0 measured 522 times and 1 measured 502 times. These results are close to a 50-50 split, exactly what we expect for a qubit in equal superposition. This demonstrates how we can put a qubit in superposition and observe its probabilistic behavior. Now let's move on to quantum gates. Just like classical computers use logical gates such as and OR gates to perform operations on classical bits, quantum computers use quantum gates to manipulate the state of qubits. Some of the most common gates are Pauli X, Pauli Y, and Pauli Z gates. H or Hadamard gate, C naught gate, which is a 2 qubit gate. The Pauli X, Y, and Z gates rotate a qubit around the X, Y, and Z axis of the Bloch sphere by 180 degrees. The H gate puts a qubit into an equal superposition of 0 and 1. The C naught gate affects 2 qubits. It flips the target qubit only if the control qubit is in the state 1. So let's look at the visual example using the Bloch sphere. Suppose the qubit is in superposition shown by the yellow line on the left Bloch sphere. So if you apply an X gate to the qubit rotates around the X axis by 180 degrees as shown in the second image. Because the qubit is on the equator, which is also a superposition state, the probabilities of measuring 0 or 1 do not change. The qubit has simply rotated around the sphere, but its distance from the pole stayed the same. However, if the qubit were in the classical state 0 or 1, the X gate would flip it from 0 to 1 or 1 to 0. Now let's look at simple code examples showing how to apply quantum gates in the first screenshot of the code. The qubit starts in state 0, then the X gate flips it to 1. Since the qubit is not in superposition, every measurement returns 1. And in the second screenshot, a quantum circuit with 2 qubits is created and named Q0 and Q1. If you apply C0 gate and Q0 is the control qubit, Q1 is the target qubit. So if the control qubit is 0, nothing happens. If the control qubit is 1, the target qubit is flipped. This is one of the most important gates in quantum computing because it creates entanglement between qubits. Now I would like my colleague Dave to take over from here. Thank you.
Would you be fine just Davis, you want me to open my own
சொல்டா
PowerPoint or
Uh,
what do you think is
சாப்பிடுறேன்.
good?
நானு சப்பாத்தி
I have.
வாங்கிட்டு வந்துட்டேன். பட் ஆனா இப்போ சாப்பிட
I mean,
வரமாட்டேன்.
do you
எனக்கு
want me to open
நான்
myself?
ஒரு
I mean,
Yeah,
FTP ஒண்ணு அட்டெண்ட் பண்றேன். அதனால அது இப்போ
that would
okay,
be
போயிட்டு
that's
good,
இருக்கு.
I think.
yeah, okay, that's fine.
ம்.
Okay, I will do it. I will do it, no problem. Yeah, so I will share the screen. Yeah, you can close the screen, no problem. Are you closing your screen? There was this.
Yeah, just a second.
Sure, sure, no problem. Hi guys. So now I will try to cover a few other important concepts in terms of quantum computing itself. So are you guys able to see my screen?
Yeah, it's visible.
Yeah.
Oh, thank you, Devashish, for that your wonderful presentation. So yeah, let's dive into quantum circuit. Basically, when we say quantum circuit, they are the fundamental elements of quantum computing. Basically, if you are running your quantum machine learning program or any other quantum algorithms, we have to execute these quantum circuits. So these are the main building blocks to be, if we say it that way. So these are the things actually that runs on quantum processing unit or any quantum computers. So these are the things that runs, right? And these circuits basically acts on quantum data, and there are a number of operations that happens on that uh, quantum data or qubits, and also measurements, etc. And so basically it is a collection of qubits and list of instructions. Okay. So the basic convention, we can see an example. There are three examples here. On the first one, we can see a simple circuit, quantum circuit. We are using a Qiskit library here also. So we are creating a quantum circuit with this quantum circuit object, right? So then we can see this Q is a quantum bit, qubit basically, and the line would be quantum register. So that would be like for that quantum qubit, and whatever comes on that line, they are all operations. So some maybe just the edge gate, or some maybe a jet gate, right? So this basically edge is the Hadamard gate, called one of the gates. You can explore more on those kind of gates. There are a couple of gates. I think Devashish also covered a few of them. So we draw the circuit and we see that the quantum qubit is passing through that edge gate, and something will happen to that qubit. Okay, so that's a few things. That's only one qubit and one line and edge. That's it. We can also have other number of qubits. Like for example, there are four qubits in this screen. So q0, q1, Q2 and Q3, right? So, and you can see there are a couple of operations that are going on. The number of gates are going on for that. For example, for QU, we have U gate, and also you can see a bit different, like C not gate. So I think these two qubits are being worked on together at the same time. So what is the convention with these quantum circuits? Basically, we always go from left to right. Okay, so evolution, basically evolution, we can say that also. So we come from left here and then we move towards the right. So basically everything start from here, so not from right to left but left to right. And so yeah, gates are chronological, they are timeless. So first we apply these gates, and then this, and then this, and then this, and finally this gate. Okay, so we can have other types of quantum circuit, more quantum qubits, more also classical registers, where we actually measure what happens to that quantum qubit after it goes through a number of operations. We need a quantum register. We need to measure it in a classical way, right? So basically, we can have a double line then. So in that quantum circuit, now we'll have a double line. These are all single line. These are for qubits, and these are for classical registers. So basically, this is going to measure state of this qubit at here. So it is going. This is basically a representation, right? Basically, but as in a physical way, that might be a bit different. But if we want to visually represent kind of in a quantum circuit, that's what happens. And for qubit one, if when it comes here after a number of operations, and this measurement will be transferred into a classical way. So right. So yeah, the quantum circuit itself is one of the fundamental concepts and very important concepts. So now if we see a bigger example of a quantum circuit, we can get two quantum circuits, a feature map and NZ. So we are going to use these ones in later on in our quantum machine learning course, as well as in quantum federated learning in day 3 and day 4, I think. So these are basically, again, one kind of quantum circuit, a bigger one. A lot of operations are going on. For example, here in this feature map, we have Q0, Q1, Q2, and Q3, right? So we are using 4 qubits there, and they are going through a number of operations. And the feature map that is basically used in encoding, maybe converting classical data representation into quantum data representation, so that we can work on the data features like, and then we can classify here and there. So this is an example of JJ feature map. Okay, there it's already in the Qiskit library, and it is based on number of features. For example, iris data set we can have like 4 features. Genomics data set we can have a different kind of features. MNIST data set have also different kind of number of features, right? And but of course for iris dataset, if we need 4 features, then we can use 4 qubits, and then we can encode the features of those one into actual representation, and then we can work on those classification or anything like that. That's the first circuit, a bigger one, JJ feature map. And there is a second one here that is also another example. This is called real amplitude. Basically, this is a parameterized circuit. So when we say parameterized circuit, basically it has a parameters where we can actually update the values based on like maybe optimization process, right? Like we feedback, okay, your classification is not wrong, it's not right. So you have to change these values here and there. So we use this kind of parameterized circuits, real amplitude. So basically here is the main thing that goes happen. We will cover these things in more detail in quantum machine learning class, most probably in day 3. Okay, so these are the examples. Basically we are running quantum algorithms in the using quantum circuit way. A number of gates are applied to qubits. There are a number of qubits, this and that. Okay, and these are mostly used in a number of quantum classifiers. One of them is variation quantum classifier. And yeah, this is basically it helps to make us with a neural network and classify things. Okay, so that's the one of the variation quantum classifier things. Now, yeah, as I've said, every time we're doing something, we have to run our quantum circuit either in quantum computer, real hardware, or we can use our simulators, right? The basic backends we have with the Qiskit. So they replicate like the features or nature of quantum hardware. So we can use, for example, in here we are using air simulator. Okay, so there are a number of ways we can run. So basically, when we are trying to run that circuit, what happens basically is we sample the states of qubit. Once a number of operations have been done, we try to sample what's the state of those qubits, and then we transfer those results into classical register. And in Qiskit, we have a primitive called sampler primitive, where there are other ways we can directly run on the backend as well. For example, here we air simulator, we are directly running it, or we can use sampler where we can pass that backend and then we can run that circuit on our quantum computer or our air simulator kind of things, and then we can get those results like here we can see for 00 we are around 508. So why are we running so many times? The one of the reasons is because their results are random, to be honest, and then there are like errors and this and that, and we try to make sure that these are addressed, right? And then we run it for a number of times, 1,000 times, 4,000 times, depending upon the need and requirement. So we can run those ones and we can get the count here. This is basically an entangle I'll cover, and it will be also covered on tomorrow most probably. Yeah, the probability is almost 50-50 here, so the state of the qubits is almost 50-50. So yeah, these are how we can execute quantum circuit. Okay. And so when we say measuring qubits, basically we are trying to measure its state. Okay, it's into classical measurement. For example, we can create a quantum circuit like this. We have qubit 1, qubit 2, and it is passed to Hadamard gate, and then we have control net operation on those 2 qubits, and then whatever measurement we have, we will be measuring register 1. So we can create like quantum register. There are a straightforward way. We don't even have to do like this. Like we can say quantum circuit and measure all, and then it will happen automatically. But yeah, the proper way is to just quantum register is there, classic register is there, right? And then quantum circuit, Q1, Q2, Q3. So we can actually give the name also. See, you can name this one your qubit, right? And you can also give names. So you can create a quantum circuit. And one of the famous, one of the general way to measure is in computational basis is in using polyjet basis. Basically, there are other computational basis also, but the way that we use that computational basis is the result will be either 0 or 1. So, but that with the probability. So either 0 with the probability of alpha square, the first amplitude of that first qubit, or result 1 of the probability of another, so e square. So this is the probabilistic outcome. And also once we measure the qubit states, it will lose its state. Okay, that's also one way so the measurement works. So we can see we have the outcome, two outcomes. So and this is where we can set up the circuit. Now there's a very interesting thing. I think Devrasis also has covered a couple of works. How do we visualize quantum state anyway, right? It's like it's very tricky. It has a superposition also. So many things are going on. So how do we visualize those kind of things? Basically, we can use something called Bloch's sphere. So basically, it's the sphere in itself, and any point on the sphere is basically a quantum state. So for example, if we want to represent this quantum state here, this is the state. For example, actually this is simple, but I just wanted we just wanted to see this tail theta and the Murphy. So that's why I was just using it, but it's only 1.5 kind of square root. It's still that same thing. Okay, so this quantum state can be represented here, and you can say this is theta, this is from this say axis, and this is from this axis, and this bar with the angle of this one, and we can represent the phi quantum state here. So programmatically also we can do that. It's straightforward, easy. First thing, we create a quantum circuit, right? So just one qubit is there, and we apply Hadamard gate. Whenever we apply the Hadamard gate, it will be in the superposition position basically. So basis state is 0 and 1, but yeah, when we apply superposition, it will be anywhere, but most probably it will be here. So here we have state vector we use, and we plot Bloch sphere with this function that is available in Qiskit itself. Okay. So and the theta and Murphy are the ones that we decide where that point is that for that qubit state. Okay. So it's a very interesting topic, Bloch sphere itself. Yeah, it's a bit tricky for multi-qubits, but for single qubits, Bloch sphere is used and to represent where it is or kind of thing. So okay. Now, now I'll just quickly try to cover two very important concepts: superposition and entanglement. Of course, you guys most probably know it, heard about it. Most probably tomorrow we have these things in more depth about the teleportation. I think tomorrow or day after tomorrow. So I've just tried to quickly touch on this subject. So basically, all the one of the superposition is one of the main concept with quantum computing that gives power to quantum computing itself, superposition. So it's like we have classical bits, right? In classical computing, every value is either it is deterministic, like a coin, flipping a coin, either it will be up or down, unless the coin is malfunction, right? It can stand sometime in the vertically. Otherwise, we will have either up or down. So in classical bit, the value will be either 0 or 1. That's straightforward. But with qubit, with our quantum bits, that's different. Their state can be in linear combination of states. Like for example, here this equation, this one, and alpha and beta are the complex numbers. Most probably you will see this equation a lot. Most probably you guys know about this equation already. But when we measure, it will always go to one of the states, and then yeah, a simple example of classical coin, up and down, 50% chance. But with the superposition, it's tricky. It's a complex number, right? So so it will be somewhere here, right? And then yeah, and we can use something like this for Hadamard gate to create a superposition, and this is exactly the plot of this one. Basically, we have a quantum circuit, coin, edge gate is applied for that one, and we just measure everything because of only one qubit. So basically, it will be in uh, this state that is seen in Bloch's sphere. And we if we run this circuit, yeah, for example, yeah, something like this state, then we will see again this kind of like 50-50 because of the superposition kind of thing it's going on there. Okay, so this is also one of the very important concept. So we most probably will cover this one tomorrow also. Another one, the last one for me, is this entanglement. A very This is a basic foundation for very quantum phenomena, because for teleportation, like super dense condition, coding, these are the um, foundation for these interesting quantum phenomena. And one of the simplest form of quantum entanglement is Bailey state itself. If we want to create something like this, we can simply like this. You have two qubit, I am qubit 1, I am qubit 2, H and C not get between these two qubits, and measure them, and then they will be in these are the pairs of bits which are very useful for teleportation. So if two people are there, if we want to send something to do teleportation, we will cover this in detail tomorrow most probably. So yeah, this is also one of the important concept. And yes, this is the key ingredient for quantum advantage. And basically, if something happens of measurement, something happens to one pair of that entangled qubit, if even though that qubit is far away, like in a distance apart, yes, we can have some kind of impact on that another qubit, or determine, okay, this the state of this qubit is similar to that kind of thing. Okay, with that, I think I have come to end of my slides. I would like to hand over to now Babo. Babo, are you there?
Yes.
Okay, thank you, everyone. I will stop sharing. Are you able to share yourself, Babo?
Yeah, you can
Okay,
stop
okay,
sharing.
okay, share. Thank you.
Yes, I'm going to share my screen. So next part actually is about the quantum noise and the error model. And next I will briefly introduce tools that to help to protect the sensitive information of the quantum system. Yes. Yeah, can you see my screen now? I think, yeah, I think it is visible now. So
Yeah, it's visible.
yeah, thank you. So next I will introduce the quantum noise and error model. So we know that the real quantum system actually are open. It means that the qubits actually will interact with the environment. So disadvantage, maybe a disadvantage we say for the quantum system is that in the process of the computation, the real quantum state will be disturbed. So in the computation, actually, after the measurement, we get the result, and the result actually is not the real quantum state in the quantum system. So real quantum system are open, and it will lead to the noise. So next, we have to know several common types of the quantum noise. The first is the decoherence, and the second is the coherence noise. So before we know the difference between these two different type of noise, we know what's the quantum coherence. So we can see it here is that the quantum coherence describes the ability of a quantum system to maintain a freeze relationship among its states. So what is a freeze? So if we can say this figure, I know that in the previous slides, we can also say this formula. That is a description of quantum states. And here, in this one, we can say e to the power of I and the phi. So the phi actually, it means a freeze of the quantum state. So the freeze actually is angular component of the complex possibilities amplitude, so that it can characterize the states. So the first describes the angular difference of the cat1 component between respect to the cat0 component. So the decoherence noise will mean that the qubit will lose the coherence. So we can say in the description, it is a process that quantum systems lose their quantum probabilities due to the interaction with the surroundings. And the coherent noise means a type of noise that maintains the coherence of the quantum states. But it's mainly from we use some systematic errors. So it will lead to the coherence noise. So if you see in the right side of the two papers, the right side of these slides, you can see the first figure actually describes the decoherence, and the second figure describes the coherence. So you can see that the right dot actually is previous quantum states, and this right dot actually is quantum state after affected by the noise. So you can see in the first figures, when a quantum state is affected by the decoherence, the quantum states previously the quantum state appears on the surface of the Bloch sphere, and after it's affected by the decoherence, it's inside the Bloch sphere. So we can say the different positions of the quantum states when it affected by the decoherence noise. So it's from the surface to the inside of the Bloch spheres. But when the noise is a coherent noise, so we can say that the quantum states only move on the surface of the Bloch sphere. So that's the difference. So decoherence make the quantum state lose some informations because previous one is on the surface, and after that it's in the Bloch sphere. So that's the difference of the two type of noise. So next, another common types of the quantum noise is the crosstalk and the measurement. The crosstalk actually, we know that when we describe these two type of noise, the coherence and the decoherence the noise applies on the 1 qubit. But if we discuss the crosstalk noise, actually you see the figure here. So it's not focused on the 1 qubit, but focused on the 2 qubit. It means that one change in a qubit will affect another qubit. So that is a crosstalk noise apply on more than 1 qubit. And another one, the last one, we say it is measurement noise. So previously, we introduced the process of the measurement. So you know that when we measure the real quantum state, actually the qubits will collapse to the cat 0 or the cat 1. So we must apply multiple times of the measurement to infer the real quantum states. But if we increase the number of measurements, it will the cost and the time will be increased. But if the times of measurement is small, the result is not accurate. So it will be a balance problem of the cost and of the accuracy. So that's why the measurement also increase the noise. So when we measure the states of the qubits, that it will introduce the noise. And mostly we will call the times of measurement it will be the shots. So when we say one shot, we means that we only measure the quantum states once. And if we say the short is 100, it will mean that we will measure the quantum state 100 times, and we will get the average values. The average values will be the values that we infer the real quantum states. Yes, that is the measurement noise. Next two, we will say, so actually most common noise we will use to simulate the noise in the real quantum system. The first is the depolarizing noise. The depolarizing noise applies in the quantum channel. The quantum channel means that such as we apply multiple gates in the quantum circuit, and the noise can be applied in each of the gates in the quantum circuit. So we will say that it is a depolarizing channel. So that's the formula is the equation of the depolarizing channel. We can say that we assume that the rho will be the original quantum state, and the P will be the depolarizing possibilities applies on the quantum state. So we will say that if the values of the P is larger, it means that the depolarizing possibility will be larger, and the magnitude of the quantum of the depolarizing noise will be larger, and so it means that the qubits will be affected more by the depolarizing noise. And yes, this is a equation of the depolarizing channel. So it actually describes how the channel transforms for the quantum qubit state into a mixture of the original state and the maximally mixed state. So original state we may say on the surface of the Bloch sphere, and the mixed state is inside the Bloch sphere. So depolarizing channel, actually we say it will be the one type of the decoherence noise. Yes, and next we can say how we can which metric will help us to measure the influence of the depolarizing noise. So here we introduce a new concept. It means the fidelity. So fidelity actually measures how close to quantum states are. So actually it will in the range of from 0 to 1. If the value is close to 0, it means that actually the two quantum states will not too similar. So if we use the fidelity to measure the effect of the depolarizing noise, and if the value is close to 0, it means that depolarizing noise have a big influence to that quantum state. And if the fidelity is close to 1, it means that the two quantum states are so close, and the depolarizing noise have a small influence to that quantum state. So you can say that is the equation how we can calculate the fidelity. So actually it is the magnitude square of the overlap, but this equation only for the pure state. And we can see in the right side of this slide, actually it's just an example of how we can apply the depolarizing noise in the quiz and how we can use the fidelity to get a result to show that how much the depolarizing noise affect the quantum states. So you can see that we can define before that we must import the library and the functions we have to use. And next we can define the possibilities of depolarizing channel, because here this example is use 2 qubit. So depolarizing noise can apply on the 1 qubit, can also apply on the multiple qubit. And you can say we can define the P1, the possibility, depolarizing possibility is 0.01, and P2 is 0.05. So here you can say that in the quantum state we have two different gates. The first is the Hadamard gate, and the second is the CS gate. So Hadamard gate applies on the 1 qubit, and another gate applies on the 2 qubit. So here you can see we apply the possibility of 1 depolarizing noise on the 1 qubit. We apply on the Hadamard gate, and P2 is on the the gate includes two quantum states. So here the P2 will apply on the CS gate. So we apply the different possibilities of the quantum noise on the different gate. And if you want to add more gates in the quantum circuit, such as you want to add the rotation gate, such as RX, RY, or the ID, you can also add them as a gate here, and you can change here. If you only want to the depolarization channel apply only on the Hadamard gate, then you can only add it here. But if you want the depolarization noise applies on the other gates, such as RX gate, you can add RS gate here and change the Hadamard gate to the RS gate. Of course, you can also add RS gate and Hadamard gate exit both here. So that's how we can add the depolarization noise to the quantum gate. And next, we have to calculate the fidelity to show how much the depolarization noise affect the quantum gate. So we have to compare. How we can compare? This one is the first quantum gate, and the gate is with H gate and CS gate is with the depolarization noise. And the second, we can create another quantum state and the quantum circuit. So in this circuit, we have the same quantum circuit architecture, but we don't apply the depolarization noise in it. And finally, we can get the different quantum gates after apply the quantum circuit, and we can use the state fidelity to calculate the ideal one and the noise one. A noise one is affected by the depolarization gate, and the ideal one is only the same quantum circuit, but no depolarization noise. So we can say we can calculate the fidelity, and you can say that it is close to 1. So because in here the possibility of P1 and P2 we set is very small, so the fidelity is close to 1. Yeah. And next is about the measurement noise. So here it's an example about the measurement noise. So we may say the times of the measurement is a short. So we can define the number of shots here. So if the shot is so small, it means that the result may be not accurate. But if the shot is so large, we can infer the real quantum state accurately. So here we can say we also add the Hadamard gates in the quantum circuit, and then we measure the quantum state. And you can see that the initial state actually is cat 0, and we apply a Hadamard gate here. So the quantum qubit will be changed to the cat plus. The cat plus actually you can see it in this equation. So when we can see this equation that actually when we do the measurement of the qubits, if we think that if the shot is very large, so the times of we get the 0 and get the cat 0 and the cat 1 actually is same, right? But here we only apply the short is 1000, and we can say the result in the outcome. So we get 496 when we measure 0, and we can get 504 after the measurement we get the cat 1. So if we enlarge the shots, the two values will be more equal. So that's the code, the example how we can apply the measurement noise. At last, I will introduce the quantum differential privacy because actually it's one of my research areas. So I'm not sure if you know the differential privacy before. Differential privacy is a one tool that can help us to protect the personal sensitive information by adding some random noise And quantum differential privacy, actually, it is based on the differential privacy. But the difference is that in the differential privacy, the noise we must edit, but in quantum differential privacy, we know that quantum have some internal noise. So we don't have to edit manually. So we can choose, we can use the quantum internal noise, or we can add some external noise. The external noise can use some mechanism from the differential privacy. So it will pose one problem because we introduce so many types of the quantum noise. So which one is suitable for the quantum differential privacy? So the coherent one, because it's introduced from the we can say sorry. So actually, it's introduced the systematic errors. So sometimes it's not random, but the decoherence actually is random. Decoherence noise, one example is the depolarizing noise. And the crosstalk, one method we must use in the quantum differential privacy is that the noise must be the independent. So crosstalk noise applies on more than one qubit, so it's not independent one, and the measurements measure each of the qubits. So we will say that will be the independent noise. So we can say the decoherence noise and the measurement noise are suitable to realizing the quantum differential privacy. So we can use the measurement noise, the short noise, another one, depolarization noise. An example is the coherence noise, an example is the depolarization noise. So that's it. That will be the definition. Actually, you may think it's hard to read at first to describe what is the quantum differential privacy. So quantum differential privacy actually realize that if I add a small noise to the qubit, so after you read the output of the measurement process, it's hard for you to infer what is the real quantum state. So you can see there M here is the measurement operators, and the TR actually is a trace distance. Distance is a metric to describe the distance in the quantum system. And here there are two important parameters in the quantum differential privacy. One is epsilon, and the second is data. The epsilon controls the level of noise you add, also control the privacy protection level. It means that if you add a large amount of noise, so we can provide more privacy for that qubit, right? So the epsilon, actually, the smaller epsilon will provide a bigger privacy protection and introduce a bigger noise. And here the delta is used to control the small possibility of the failure in the privacy guarantee. So in most cases, the delta is so small, such as 0.01, 0.05. It is so small. So that is just a quick introduce of the quantum differential privacy, and it can be a tool to help us to provide the privacy, especially in the quantum federal learning. So I will introduce it in more details in the day 4 when we introduce the quantum federal learning. So yeah, I think that's all from my part, and the next is about the hands-on component. So I think it may be moved to the next one.
Thank you, Baba. I will take over from now. Let me share my screen first. Uh, yes. Are you guys able to see my screen? Just let me know.
Yeah.
Yeah, thank you. Uh, Hi, everyone. Welcome to this hands-on session on Introduction to QuizKit. This session is designed for a very beginners kind of thing. So we do, if you don't know anything about quantum computing or you do not know about deep physics, quantum physics, or heavy mathematics, we still able to follow along, and we will build intuition step by step using a live code. So by the end of this session, you will have able to learn how to build and visualize single and multi-qubit circuits and simulate the state evolution and measurements, like my colleagues already discussed in the previous sessions. And in the end, if the time allows us, then we will also see how to run our own small circuit on real quantum computers, which is provided by IBM. So we will start with QuizKit. And why QuizKit? QuizKit is generally is very recognized and open source platform uh, from delivered by IBM for quantum computing in Python, basically. So with QuizKit, you can build quantum circuits as a Python objects, visualize those circuits, simulate quantum behavior on your laptop or in the cloud. So and when you are ready or when you are ready to or you learned, you can run your quantum circuits on real quantum hardware via IBM Quantum. So basically, this is a website from the IBM Quantum platform. So if you see, this is their base. This is their I can say very entry, and we will directly go to the quiz kit part. So the quiz kit, as I already told you, is like the mm, open source sorry, software, which will help us to build even starting from our quantum chemistry thing, or I can say quantum physics, and even machine learning, predator learning. Currently we can do lot of things which we can do which we able to do in classical computers also. So outside this if you want to uh, your circuits on a real quantum computer, you need to sign in first. IBM will give you this. I already signed in for this, but when IBM already give you the 30-day trial, which gives you around $200 to have the its cloud services. But for the quantum platform, you will only get 10 minutes per month. So whenever you run your quantum circuits on the quantum IBM platform, it should be error free. Otherwise, you will lose your precious 10 minutes, which is very, otherwise it is really costly to have get extra. For example, I think 1 minute is around 100 and something dollars, or maybe above $50, something like this. So so let's start with the quiz kit. And other thing is, if you are able to, if when you are able to run the want to run the Quizzkit, you have multiple options. For example, you can use Google Colab, you can use IBM on Quantum Lab systems, and you can also use something called QBraid. This is also something like Google Colab kind of things. But here you will see you can run. This is a dedicated platform for quantum execution kind of things. And yeah, and if you have a powerful machine, powerful means really powerful machine, you can run your complex quantum algorithm as a simulation in your local systems also. And I will go through one by one. And in the end of on this session, I will share this exact code with you guys, which will help you to do help you in to do task sheet one, which I already send you through email. So hopefully you will get something from this session. Let's start with this. So uh, yeah, basically, we need to install couple of things before we start in any, even in your local or KubeRed or in Google Colab, starting with QuizKit. There are two ways to install the QuizKit. Is one is the QuizKit only, and there is another way is to use the QuizKit visualization. What this module do is it will help you to visualize your quantum circuits, your graphs, everything. And there is another thing, QuizKit AER. AER is your software, quantum soft uh, is a software which you can say it's a software version of your hardware, quantum hardware. So this is QuizKit AER is responsible to run your quantum simulation on your local machines or in your classical machines. And QuizKit IBM runtime is we use this when we want to run our circuits in real quantum systems, and rest of these things are necessary, the dependency. uh, then uh, then first we need to import couple of things which are like maths, numpy. These are the normal imports for QuizKit. So yeah, and after that, we need to import the quantum circuits. The quantum circuits are a main class for building quantum circuits in Python. We will use it to define the qubit, gates, and measurements. Then we have a transpile. Uh, transpile is a Qiskit compiler. It takes our high level circuits and rewrite into a form that specific hardware, because there are a lot of different type of hardware available, and we need to transpile to a specific hardware. So or we can use it for simulation as well as for real quantum systems. So it may change the gate orders if or choose native gate sets, which means like very basic gates. And it also maps your qubit to your hardware. And then we need to also need parameters. Parameters let you create the parameterized circuit where some gates angles like theta are symbolic or and can be filled later. I will explain in the code. This is really useful for the experiment where we want to scan parameters or optimize it without rebuilding the entire circuit each time. Then for these imports are for the visualization, basically for example, plot histogram is for turn your measurement in results into the bar chart showing how often each bit string appears. Then other is the Bloch multi-vector. It will visualize your single qubit state on the Bloch-sphere, which is a geometric picture of all possible one pure state, as we see in previous sessions. And the other is plot circuit. It shows how logical circuit maps on the physical layout of specific quantum device. And this is state vector. This state vector is uh, is represent, like I can say it represent full quantum state, that is amplitude vector. It's useful when you want to more detail just than the just measurements results. For example, plot or inspect the amplitudes. Then this is very important. AER simulator. Uh, this is this is our software quantum computer. It is highly configurable. We can use different devices with different backends. We can model the noises here using this, and we can use different type of, even this let you use your classical GPUs and CPUs. Uh, and this is very important for our simulation. And other things are the noise models, and like Bao explain the depolarizing error. And this is how we can introduce depolarizing error into our codes. And the last thing is fake provider. This is the fake. In other words, I can say it. These are the uh, the real like copy, or I can say the image of real quantum systems or real quantum hardware. For example, quantum hardware A has some properties. We can mimic same properties using fake providers, which will help us to do our simulations to test before deploying on real quantum computers. So and this is the main import which we will discuss, which we need today's for this session particularly. So in the then yeah, of course. And one very important thing to do Qiskit thing. Qiskit is evolving software. It might be possible whatever code I will show you right now, it will work right now. And if when you will install your Qiskit, it might not work because it might change. Qiskit team will update something and it will break its functionality. So be very careful whenever you want to do anything with Qiskit. You have to stick with one single I can say version. For example, currently is 2.2.3 something like this. But in my own simulations, for my own study, for my own research, I use 1.4.2, which is I think last year's version. So you will lose some of the latest innovations or latest I can say functionality, but it will be much more stable than the latest version. So this is we will configure. This is how we will configure and set up our backend, and we will use it to use it to execute our circuits. So whenever you see simulators dot run, think think of run this circuit on my virtual quantum machine. It is behaved like this way. So let's start with one qubit thing. It's a simplest possible quantum circuit. So this is how it looks, and I will show you. Yeah, uh, this is first we will define the quantum circuit. This creates a circuit with one qubit and one classical bit, and we name it as a one demo bit. And by default, the qubit starts with a state zero. That means a bracket zero. And this will gives you this lines will gives you the X gate, that is in classical one is not gate on a zero qubit. So when we want to measure it, it will look like this. Oh, sorry, I need to run all this first. Mhm. Yeah. By the time it will run, I will explain the each and every line. Uh, the QC underscore one dot measure will measure your qubit into a classical bit zero. So converting your quantum state into a classical bit zero or one. We will see how it will change. Yeah, you can see my current version is 2.2.3. So you have to very careful when you are running your code, which versions you are running. Maybe in future coming sessions, we might not need 2.2, might we need 1.4, because quantum machine learning, Qiskit enabled quantum machine learning still uses 1.4. Similarly, in even in federated learning sessions, you might need a different version. So be careful about this. And while you importing, be care about you can see the same exact statement, just you can might see the change in either underscore or something like this, which is really hard to find sometimes. So let's run this. You can see we are measuring it, and we are plotting, or I can say we can tell the Qiskit, please print how we use print commands in uh, in in our Python. So this thing measures the thing, measure your qubit into a classical bit, and this will tells the Qiskit to draw the circuit using matplotlib, that is MLP, and this gives you the nice, as you see, nice circuit diagram. So we can see the qubit line, X gate, and the measurement. Whenever you see in any circuit, whenever you see this symbol and it is grounded to the classical bit, that means it is measuring your current qubit. So for example, if I want to change to head gate, so I just need, because Qiskit has instead of head gate as a H. If I change to H, the same thing will behave differently. Now this will the circuit behaves differently. You can see this way. So for the next one, yeah, let me first run, then I will explain everything. Yeah. Uh, yeah, this. If you let, yeah, uh, here we are just converting our entire circuit into into the hardware level gates, basically the basic gates of hardware. This compiles our high level circuit into formed optimized, or I can say whatever hardware we are choosing, depending on our hardware, it will I can say, in other words, to decompose it into a smaller chunk. For example, if in real world, if we have a very large amount of data to send from here to another city, we system distribute or make a small packet out of it. Similarly, something it is exactly not a dividing, but it is decomposing into a smaller or a simpler gates, or a different gates, which helps us to, which helps us as well as the hardware to compile, or to run and to execute the code. And this is transpilation is a very critical, or I can say crucial step in Qiskit. So then the next then you see the simulator dot run. This is where I already told. This means we want our circuit to run for the 1,000 time, as Baobab told you earlier. If you change this, this will give you the reliable, or if it is too low, it might be a not reliable results. And the drawback of this is it will increase your compilation time. For example, you want, okay, Navneet, I need very concrete result, so I will might make it like 10,000 shots. In This is a very simple one, it might be done very easily, but when it will be a very complex circuit, it will be I can say takes a lot of times. It might takes days, maybe 3 weeks, 4 weeks to just run the single circuit, or your entire code, just because of this. So we have to choose very carefully, like how much shots we we want to give. And here the dot, the result, basically this will gives us the result object once it will done. Once the entire uh, simulation is done, then it will gives us the object, Python object, to which contains our results. Then we have another crucial method called get underscore count. This collects the measurements and return the directory, the mapping each outcome like 0 or 1 to the number of times it observes. For example, if like I already changed it to 10,000, that because of this thing, it means it observe our circuit, circuit are observed zeroth in 5106 times, and for the one, it is for 4894. It is like this, and this will give you uh, the histogram of the entire to show you how it visually looks like. Yeah. And if you think, okay, we can change, we can if you want to change, and let's say change to one, and we will see how it behaves differently. See, because we have used a hard mud gate, it converts our qubit into a superposition. Now, right now we are able to see only one I can say one measurement. When once we if we change the gate to hard mud gate, then it will gives us the qubit position in a superposition. So Hadmard gate generally gives us the superposition. So so it is a really crucial thing. So and this shows that it is a 50-50 probability, almost 50-50 probability. Because of this, we if we increase it to maybe 10,000 again, maybe it will give me some different. And if even an how many number of times I will run, it will behave differently. So this is why we need a shorts. So how concrete our results is. So the more you will, it will always give you a different result. So we have to very careful to this. Basically, X gate is a very deterministic, and the Hartman gate is a probabilistic mixture of the state zero and one. So let's move to our two qubit Hartman and NOT gate. So uh, this will show you how they can become a correlated with each other. Let's first let me then run the thing. Yeah. We can create using this we can create two qubit. That means two qubit, two classical register a bit, and we and this is just a name for our circuit. That's it. It does not have any value or any impact on our circuit. So you can write whatever you want to do. Basically here we are telling put qubit zero into a superposition. Then we are saying here please add a controlled NOT gate, that is CX gate, to 0 and 1, and where the 0 is a control and Q1 is a target. If 0 is if qubit 0 is at state bracket 1, I can say, and we flip it to qubit 1. If the 0 is at a state 0, then we do nothing. So if you see, this is how it looks like. And these this is the key of two qubit gate, and how we create a correlation between and correlations and entanglements. Then we measure both of these qubits into the classical bits, and again you see when we draw it, it looks like this way. So what we do is we put our qubit 0 on Hartman gate, and then we use the control NOT gate. Then we measure both of these two. Further we will see how it changes the behavior. Yep. Now you can say you can see uh, almost outcomes are either 0 or at the 1, but you cannot see 0 1 or 1 0. Intuitively, the hardmate gate on qubit 0 creates the superposition, and the CX copies that information into qubit 1, which makes them correlated. So basically, whenever we put hard mid gate, and then And then we put our CX gate, control not gate here. Uh, these two qubits now are correlated to each other. This is very close to the entangled state. We will talk about more when we discuss further in Bell state later. So you have to very careful when in other words, I can say, just remember this. Here we are only getting two states, 0 0 and 1 1, and later we will see how we can get other two states also. And let's see how sensitive the quantum circuits are to the small changes. Let me first run this also. Here is a key difference is we have added a QC modified uh, Hartmut gate to another qubit also on basically the qubit one. And if we and the rest of the thing is same. If you see, we just add another gate here before the measuring the both of the qubit. So now we will see how it changes everything. Yep. Now you can see all four states. So compared to our previous histogram, you will see that the distribution of the bystrings has changed. You can clearly see now everything is different rather than here. This shows that even a single addition of gates, like one more Hartman gate, can significantly change the overall behavior of our circuit. So when you are executing the large real world problem to solve the real world problem through quantum circuits, you have to very careful where and how you want to add or remove any gate or any measurement, or how to change the behavior of because that particular thing can change the entire behavior of your circuit. Now we will visualize how the fake hardware, or I can say the fake backend, but in other words, we can say the fake hardware. Here we will ask the system, okay, we want to use or we want to mimic the hardware which has minimum of 5 qubit. So you can put maybe five, you can put 144. Right now there are some quantum computers which can have 156. There are IBM's computer which have 133. It depends on you. So the least one we will take for this simulation is five. So so basically, whenever you use this one, you cannot use your qubit more than five, because it has this creates a I can say simulated hardware which only have 5 qubit. If you have some circuit which needs more than 5 qubits, it will not work in it on this. So s- yeah, so far we have treated the qubits as an abstract index 0 and 1 if you see above. But on the real hardware, the qubits are laid out physically. I might not able to show you how that. Let me think. Yeah, this is how the qubit I can say maps is in the system in IBM Fizz that has a 156 qubits. And if you see, you have to choose the least amount, the qubits which has the least amount of error, as well as the connected with each other to execute your system. For example, here this shows that this and this qubits are not connected with each other. So you cannot use this and these three four qubit together for your execution. This is a very low level programming when you choose which qubit you want to choose, or which map you want to do. So just this is for your information. I don't think so you need for your basic, even for your full 5-day sessions also. Yeah. So similarly, this is how we see in where it is. Sorry. Uh, this is how you see in the real world, but these are the interconnected with each other. The similar thing, because this is have the 5 qubits, so these are interconnected with each other like this way. So let's visualize the circuit layout using the fake hardware backend. So here's what's happening is the generic backend V2 creates a fake backend with five qubit arranged and connected like a toy device. It does not run a real quantum processor, but it behaves like a real quantum in terms of topology. So in Qiskit, the qubit we refer in our code like qubit 0 or qubit 1 called the logical qubit. When we transpile of for the basic for a basic or a specific hardware or a backend, the compiler must map those logic qubit in a specific way onto an actual physical qubit on the chip. So which might be a number differently and have a limited connectivity. For example, if you see here, uh, for here, these three do not have a connectivity with each other. So we have to very careful, as it should be connected as well as uh, uh, have a other way. They should it should create some connection with each other so that we can use the logical we can use it as a logical qubits. So and, yeah, and for visualizing for the mapping, it is the same how I tell you before. It is like um, the draw thing. So it's just telling us which logical qubit is placed on which physical qubit line on a hypothetical chip. So basically, you can see this 0 and 1 is connected directly to each other. This is very important for real hardware because only certain pair of qubit are directly connected to 2 qubit gates like CX 0 and comma 1. Uh, that means that means you are very careful when we want to deploy our real quantum on real quantum systems. How our circuit should behave. It depends on these logic, I can say, or these connections basically. And the transpiler will sometimes introduce some extra operations to swap or to with sorry with respect of these connectivity constraints. Yep. Then let's see how we can create a parameterized circuit. So basically, imagine in a such a way you have some rotating dial, and how you rotate, it will behave differently. So the rotation angle, or I can say if you change the angle of the rotation, it will behave differently, and you can change the entire circuit in unlimited, I can say infinite ways, but there are only not a very limited, but it is a quite limited, uh, quite limited. I can say the real, or in other word, I can say provable quantum states. Let me first run this, then I will explain what is going on in these things. Yep. Yes. Here we will create a parameterized circuit and on 1 qubit circuit using the rotation gate, that is Ry theta. This is just a name. Basically, this parameter is telling us this function is telling us, okay, create I can say a circuit uh, which 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 needs a theta, and we will change the value of theta. We will see later. This is like as I already told you, this is like a quantum dial that we can turn smoothly from 0 to pi, basically. So if we run this, then you can see here the first line, the theta equals to parameters, creates the symbolic parameters mean theta, and this circuit known there as a placeholder angle, but we haven't set any numerical value yet. So when we change, for example, first we will create uh, a basic circuit, then we will change its a value later. So for this, here's what's happening is it applies a rotation gate around the y-axis by angle sorry uh, by angle theta, and uh, yep, on theta as well as and when the theta changes, the qubit position on the Bloch sphere moves, and the possibilities or and sorry, the probabilities of measuring 0 and 1 state also changes. For example, if you see there is another platform provided by IBM itself, you can see this is how different uh, I can say qubit or a different quantum states looks in inside the blocksphere. You can use, for example, RZ. This is also this gate. RZ gate is telling us that the rotation is happening around the z-axis. Z-axis. So, so if you see, it is like this. So it behaves very differently wherever you put. So if you see, it is like this. eh, You can see it behaves very differently wherever you see. So yeah, then let's. This is how that circuit is there. Let's change some specific value or give some specific value to the theta. This function gives you some values between 0, 1.5, and 3.14. They're basically 0 to pi. So, and this binds the concrete value to your theta and producing the new circuit called like bound QC, and with the fixed number of rotation, numeric notation. And our simulation dot run will run this circuit for 1,000, or here I put like 100 shots, basically the 100 times, and our result method will store those results and gives store, and get count will gives us the how many times we are seeing the state one, as well as when the theta is at 0, we can see the probability of having a state 1 is 0. If the theta value is more than 1, basically 1.5, the count changes, then count changes. You can see that is like, then the probability of state having a state 1 is 47%. If we rotate fully to the pi, then again having a probability of state 1 is 100%. You can change it. For example, I can change it to 0 point maybe. Let's see how it behaves when we put 0.07. See, yeah, again, see the probability of having state 1 is decreased to only 24%. So this is like when the theta is 0, it's always gives us the state 0. This is how it shows. And when the state is pi by 2, then the half is 0 and half is I can say the 1. And if the theta is pi, then we can see that all the probability of having the state 1 is always 1. So let's see how uh, how the probability of the measuring 1 as a function 0 in plotting also. Yeah. This if you see, this gives us a smooth curve showing how probability of getting state 1 changes as we rotate the qubit. Yeah, the more we rotate, the more probability of getting 1, the higher the probability of getting the state 1. So another is to yeah, another thing is to how to visualize on Bloch sphere. So uh, what's happening here in this one? Let me run first and I will explain. Yeah, yeah. Here we built a small circuit that applies that's rotation on theta as well as rotation on y-axis as well as on z-axis. So we will have basic circuit ready. So this is a function for that circuit where we have theta on rotation on y-axis and the rotation on z-axis. Then we want to visualize, and uh, uh, then basically the state dot from instruction gives us or I can say that take the circuit as the state vector state preparation instructions and simulate it in a ideal or a noiseless cases. Basically, noiseless is when there is no quantum noises. The quantum noises which Bao introduces in our previous lecture. So, and this is how it shows, and there are lot of this is a static image, but as I told you, you can play with this with these probabilities based on your values. And if you want to run exact same code, you can copy your Qiskit code, as well as there is something called OpenQASM. This is the very low language, or I can say a type of something like machine or assembly language kind of thing. But this is when you need very uh, precise, or I can say precise functioning, you can do this. Otherwise, you can use Qiskit, which is more commonly we use in our research as well as in our day-to-day programming. So whatever you will create here, the corresponding gates can be I can say coded automatically here. You can copy this, and if you run here somewhere, it will gives you the exactly same thing, whatever you are seeing here. So yeah, you can see the state vectors also in this. So these are the state vectors probabilities or amplitude, I can say. Uh, and yeah, how we can run if we have a more than two. Basically, whatever we have done is one qubit operations. If we want to run for more than one, so uh, let's do that. For now, it's time to design, like I told you, design a multi-qubit circuits. To For that, we will have this code. Basically, here we are using the three different qubits. You can change when you are doing it by yourself. You can play with the number of qubits. Then you have to change here also, and you can see how it behaves differently. And here I pick number 3 qubits, then we add the hard mid gate, then X gate, and then CX. And if you want to add, you can also add maybe the RZ, basically the rotation on uh, RZ gate or RV gate, whatever gate you want to add, you can add, and then try to predict which byte string you expect to see the most frequently, and then then run the simulation cell, basically. Then once you fix your circuit, and this is how this circuit looks like. If I want, okay, I want to uh, again put some circuit is uh, then I will use uh, why then it behaves different. Oh, or maybe there is some yeah, you can see this is how the circuit looks like now. You can change according to your experimentation, and we then after this circuit we can see how that simulation looks like. And if you increase this shorts to higher number, you have to wait for a couple of seconds to depending on your machine. It might take longer to run. So this is the bystrings. You will see now. We will see how the bell state and basically the entanglement, how entanglement works. We will finally the formally construct one of the most iconic the quantum states. We say it as a bell state, which is the which is like maximally the entangled pair of two qubits. If we run this, you can see this is our bell state, basically where you have where you have a two qubits having I can say one having a first qubit have a hard mode gate, then we use the control not CX gate, then we measure the both the qubit to the classical register. And when we run this simulation, uh, uh, we will see the probabilities of calculating 0 and 1. You remember previously we are only getting either 0 0 and 1 1 here. Here without any I can say without any other modification, you can see these 50-50 like I can say probability of having both of these states, and probability of having other is totally zero. So what's interesting here is each single qubit looks like the random half of random half 0 as well as random half 1, but together both qubit are perfectly correlated. So whenever you see the first qubit as a 0, the second qubit is 0. When the first qubit is 1, then the second is also 1. So this is how we simulate the behavior called entanglement. So you basically you can't describe each qubit separately. They share a non-classical correlation at the level of quantum state. Here till now we have clearly explored the superposition and entanglement using our uh, classical simulators basically. So what if these whatever we have seen till now, it is like very without any noise, or without any interference or any interaction in the environment, basically in the quantum system. So the in real world, this is not possible because the real quantum devices are noisy and gates are imperfect and measurements are not exact. This and this will be our final part for our our session. So we will add in this we will add depolarizing noise to our the bell circuit. Basically for this above circuit we will add depolarizing noise, and we will use the different number of shorts also to show how the different shorts behave differently. And finally we will compute the fidelity to see how close noisy distribution is to ideal Bell's distribution. So for what for this first we have to initiate our quantum noise model, basically where what it is doing. for P1 qubit, the error probability of for single qubit uh, Hartman gate uh, gates like Hartman gate is P1, then P2 is the error probability of two qubit gates like control not. And, as Baba already mentioned about what is basically depolarizer noise, but still uh, I will mention this. This means the probability of P1 and the state is replaced by the completely random one qubit state. Otherwise, the ideal gate is applied. The same idea applies on the two qubit depolarizing error. When we attach these error to as well as Harmat and CX gate in the noise model, we will see how it changes. Let's run this and a little bit I will explain this. Basically, here we are again developing the Bell state with the noise, but and here we are initializing our depolarizing noise. Then we transpile the circuit. Then we run our simulation for the n number of I can say shots. And here the probability we already get from previously. So we can see how that thing behave differently. Let's see. Okay. Oh, sorry. Yep. Here, yeah, it's you can see when the noise when we have a probability of having a 0.01% of in single qubit and 0.1 in two qubit, the fidelity is maximum. But the more we more we increase the number of shots, we generally tend to get better results. And this is how this is how it gives us uh, I can say the counts. Like if you see the every counts is different for every noise probability. So the more the noise in the system, the less I can say the fidelity is. It is like this. Yep. Uh, yeah, I can show you in how it in histogram also. Previously, we are not able to get 0, 1, and 1, 0, but here you can see also that this gives us all four states. This is not this is not an ideal case. This is something like how the real quantum computer behaves. So, in other words, I can say this gives us one specific noisy, I can say, uh, behavior, that is when we are at uh, 0.05% of probability of noise at 500 qubit, sorry, 500 shots compared to our ideal Bell state in part B. We can still see 0, 0 at the most frequent outcomes, but now we also see the 0 and 1, 0, 1 and 1, 0. Uh, and this has a leaked this probability has a leaked from the ideal outcomes into the non-ideal ones because of the noise, because of either if it is if everything is perfect, then these two things never appear. So this happens because of noise, and this is how the real quantum hardware works. So still we have little bit time before I will ask for a Q&A. Uh, I will quickly show you how you guys can run your quantum same Bell state in real quantum computers. Basically, if you see this, this is the we need to import the runtime. Uh, Sorry, we need to install the Qiskit runtime, and we have to import the Qiskit runtime services. So for that, we need a channel. We need a channel for specify the channel. Earlier, there are two channels, but right now you can use IBM Cloud, and for everything you will get from IBM is when you create the account in IBM Quantum Platform. So when you click on when you reach here, when you will see here, and you have to click create. Then you have to give some name, for example, test one for here, and create your API. Then copy your API and just paste it here. For because of security purpose, I will not use my API here. And then you have to use your CRN number. So from where you will get your CRN number, it will be here. When you see your instances, your CRN number is here. You have to replace this CRN with this, and then this particular command will look for the least busy, because the quantum computers are very limited, and uh, a lot of people are trying to use it. So it will find which are the least busy quantum system, and it will gives you that particular. We already run this same code uh, in early morning. I will show you how it looks. So here we will put this at that time. Uh, if at that time we have the backend is the least busy backend is IBM Fizz. So when we load this thing, the entire Bell state works on real quantum. Then it's this is its instruction address, and then this will gives you the job ID also. This job ID is you can look into once you uh, run your quantum job. You can see it will populated here with your when you created what is your job ID status and how much uses out of 10 minutes you have used. You will see my maybe 2 second, maybe 3 second or something like this. So and this is on the real quantum hardware. If you see this code and this code, this is exactly same, but we can see clear difference in the states. Yeah. So this is hope you learn something. If you need if you have any problem, you can reach out to us, and we will provide you the link for the discussion forum also. You can discuss with that and that, and I will share this code with you, and you have to do all of this by yourself as a task sheet one. Today is just for example, that's why we cover all of these things, but from tomorrow onwards you have to do some coding by yourself also. So thank you for my side. Yeah. Yeah, if you have any questions, you can raise your hand and we will have one by one. Uh, yes,
Hello?
hello. Yeah, Russell. Yep.
Excuse me, I don't have email from this conference. I take the email from my friend.
Okay.
Why?
So, okay,
I
okay.
I
You
don't
don't
receive
have. Can you
anything.
send? Can you can you send me send us the mail?
Where
Uh,
I sent you?
Uh, I will share the email address to you so that you can send us.
Okay.
Yeah, if you can see the chat, I will share you. Yes. Okay, okay, okay.
There was no chat in this conference.
Sorry.
There was no chat in this screen.
Yeah. Okay. 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 Mm, I think you guys need to send me any a mail on this. Uh, can you guys see in the chat?
Actually, we can't see the chat. It says chat isn't
Okay.
available.
Okay. 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 Sorry for that.
Yeah.
Okay. So uh, I will put it on Word so that you guys can download it. So, sorry, you can see it. Are you able to see this thing? Yeah, this is the email. If you have any problem with the sessions, I basically if you although I whatever who's ever registered, I send the email to everyone. But still, if you not got, maybe if you can check your spams, because I heard that maybe this mail is going to spams directly. So
Excuse me, I check all my
okay,
inbox, important,
yeah,
spam, draft,
okay,
all, but there
okay,
was
okay,
no email received.
okay, okay. No
So
problem.
thank you for this mail.
Yeah, yeah, yeah.
I
If you
will
if you
take a picture and will send to you something to send me back the invitation.
Yeah, if you just send me your name, your email address, and
Okay,
your supervisor name, your course, your university, and the country. Basically, the form. Basically, I will put you in the mail list again.
thank you very much.
Yep, yep, yep. And the and you guys need to do task sheets, which I already sent it you through mail, and I will also send you the link for the discussion soon, so that we can discuss there. And if you guys have any problem, you guys can send or ask us whatever questions you need. So this is any other question?
For me, no, thanks you.
Yeah, okay, thank you, thank you.
Navneet, I have a question.
Yeah, please. Yes.
Just first, I want to say thanks as well for doing the presentation. It was really good.
Mm.
I guess my question is about, is there any rules of thumb for the number of shots we should use when running our simulations, or is it very circuit dependent?
It's circuit dependent, because you might I can't say that okay, you use 10,000 or you use 1,000. Maybe, for example, I am using quantum machine learning. Maybe in quantum machine learning, because of
Yeah,
its inherent nature, machine learning can learn lot of things by itself, and you
yeah,
don't need more than 1,000 or 2,000 circuit. Maybe in some other if for example in chemistry, in quantum chemistry, where you has to
Yeah.
very accurate, you have to run maybe 10,000 times, 20,000 times. It's not generally in a thumb rule, but it's how you have basically we have right now classical computers to do simulations. So we have to keep in mind that whatever hardware we have, whatever possibilities or power we compute power we have to deal with that. Maybe
Yeah. So
same result. Yeah, yeah, yeah,
yeah. So I was training a VQC, and it was I
yeah,
think like between 4 and 6 qubits, and it wasn't
yeah,
too deep. But I think I
yeah.
just left it like standard. I think it was like 1024 shots or
Yes,
something. But
yes,
I
yes.
guess I'm asking like without actually running the simulation over and over with different number of shots,
Yeah.
is it yeah, a bit hard to know how many shots to run, I guess.
Yes, yes, yes. I have, and shorts also gives you a little bit of error mitigation also.
Yeah.
Very tiny thing, error mitigation, but it is a very early thing to do without any I can say to introduce any error mitigation technique in your circuit
Yeah.
by just using the number of increasing the number of shorts sometimes give you the better results. And because
Right.
every time same kind of error does not affect same critical component of your circuit. Maybe in first run it will attack in some different way. In
Yeah.
second run and second it is like this way. So sometimes I'm not sure, saying that it is the thumb rule, but it is also
Mm.
helping us to get better results sometimes. So
Yeah. So
in
it's
general, yeah, there are some papers who says that uh, quantum machine learning can learn from noises also to get a better results.
yeah.
So yeah, yeah.
Yeah, so I guess it just depends how much time we have on our hands as well to run
Yes,
the
yes, yes, yes.
yeah.
My simulations sometimes run more than 2 or 3 weeks.
Oh
So
wow, okay.
yeah,
Yeah. No worries. All right, thank you very much.
yeah,
Yep.
yeah. Thank you. Any questions? Any? So if you guys don't have anything, please you can either you can mail here or just wait for us to send you the discussion form link to put your question there, and we our full teaching team will try to help you out in that. So I think it is almost 9 now in Melbourne. So it's end. Yeah, yeah. So thank you for joining today's session, and we are looking forward tomorrow to get you join us in another session, which is around the quantum cryptography, entanglement, and other related stuff. And I will see you on day 3 in quantum machine learning. For then, thank you all. Thanks for joining.
Thank you so much.